Hello everyone again. We had spoken about compressional warming, and now we're going to make things a bit more specific. When we go back to look at soundings, we can look at the fact that the environmental lapse rate in red on the sounding, the temperature of the environment on the sounding, is actually a notation of expansional cooling throughout the vertical profile of the atmosphere. So while we just learned about expansional cooling, now you're seeing a graphical representation of it in the atmosphere every day. And I want to contrast that with another process that we're going to name now. You've already learned about it, now we have to name it. And that process is called the adiabatic processes. The adiabatic processes are just a fancy word for the expansional cooling and the compressional warming of the parcel alone. So while you can look at the sounding and you can see expansional cooling in the red line, now you can also look at the sounding, we'll get to it soon, and look at the adiabatic cooling of the parcel alone. So adiabatic processes talk about the expansional cooling and the compressional warming of parcels alone, and the fact that those rates of cooling and warming can happen at different rates. We'll go into all the specifics about it. That's what I just told you. So that's what I just told you too. So we can predict the rising and the sinking of parcels within the environment by comparing the lapse rates in red of the environment to the lapse rates in yellow of the parcel. And we're going to get there by the end of the chapter. This part of my lecture varies a bit from the book. It puts things in different order, and I hope this is an easier order for you to understand. When we talk about an adiabatic process for the parcel, it follows the rules that we've always talked about for the parcel. It follows the rules that the parcel is its own little balloon, imaginary balloon in the sky. And then by saying that it is an adiabatic process, we make the assumptions about the process a little bit more strict. And the assumptions are that that little balloon does not exchange any matter, so any molecules, does not exchange any molecules, and does not exchange any heat or energy with the outside environment. It's its own little balloon. And we talked about that when we talked about expansional cooling and compressional warming. Now, what does impact the parcel is just like we talked about in expansional cooling and compressional warming. The only thing that impacts it is the pressures from the outside environment. And they impact the temperature inside the parcel, and they impact the volume in the parcel. So we're just putting names to things we already studied. And to expand it out a little bit more now, we can say this, that all condensation is the result of expansional cooling. But not all expansional cooling results in condensation. Sometimes you just can't get condensation, and you already know why. You already know that you need two things for condensation. You need that cooling, and you need the condensation nuclei. Well, sometimes after a blizzard blows through, it has taken so much dust out of the environment that there is very little condensation nuclei left. So that's a time where you can have really bone-chilling wet cold, but you don't have clouds because you don't have enough condensation nuclei. Sometimes you can go the other way, and you can have so much condensation nuclei that you can't drop the temperature down to the dew point before the parcel gets so dense that it starts to sink. And that's what happens with the smoke plume that you're seeing over here. That smoke plume is so full of condensation nuclei that it's really easy for the smoke plume to sink before it reaches the dew point temperature. Let's go over a few other things as well. That fire plume also has another factor going for it. It's very dry. And you know that when a parcel is rising, it will expand and cool. If it's rising and it's dry, it will cool faster. Just like the dry soil in our radiant energy experiments cooled off faster than the wet soil, or it should have. It's really hard to make that experiment work. We say that dry parcels are unsaturated. We say that they lose warmth easily. And in doing so, they come up with a rate that is very set at 10 degrees Celsius per 1,000 meters. The temperature drops in those dry, unsaturated parcels by 10 degrees Celsius per 1,000 meters. And I want to point out to you that you may say to yourself, well, excuse me, it's a fire plume. It's actually pretty hot. What are you talking about that it's dropping temperature? I understand that all fire plumes are hot and they're dry. Some are hotter and drier than others. And so while all of them will rise and expand, they will all cool because that expansional cooling is so important up in the atmosphere. And when these cool and these fire plumes cool, they get more and more dense very rapidly with all the soot. So I hope that helps to explain a few things to you. That adiabatic lapse rate is a dry adiabatic lapse rate that lapses and declines in temperature by about 10 degrees Celsius per 1,000 meters. Let me explain it to you. If you start at the surface at 30 degrees Celsius, when you go up 1,000 meters, you will be at 20 degrees Celsius because the dry adiabatic lapse rate lapses at 10 degrees Celsius per 1,000 meters. Another way to keep that in your head is to keep a visual picture in your mind that these lapse rates are generally seen in the afternoons when the ground has gotten very warm and the wind hasn't picked up yet. It's very still, very hot. The wind hasn't picked up, so you haven't got a lot of mixing in that environment to mix the hot air with the cool air above it. So all you've got is very, very hot air on the surface and cool air above without mixing. Kind of like the experiment that we did where we showed the hot air that was not mixing in there. A way to remember this is to think about the afternoon siesta and the guy kind of laying back and relaxing and taking a snooze. He's kind of laying down later. That's for lapsing. The later part is for the afternoon. So lay down later and dry off all the sweat from the day. That's to remind you that it's a dry adiabatic lapse rate. And you can think of larger lapse rates, lots of loss of heat on the lapse rate. So this dry adiabatic lapse rate loses heat more quickly, just like dry soil loses heat more quickly. Hope those mnemonics will help you. I've already explained this to you, and I'll meet you on the other side.